For this next example, I want us to draw a graph that systematically generates all possible outcomes when flipping a coin 3 times. We did this in finite math when we were working with probability, right? So our domain is just heads or tails. So if I flip a coin 3 times, first I get heads or tails, then I get heads or tails, right? Then I flip it again, and for each of these options I get heads or tails. And we would use this to figure out what all 8 possible outcomes were. This graph is an example of a tree. A tree contains no cycles. Cycles are when an element either loops to itself or loops to another element and back, right? We looked at these a few slides ago, but this is an example of a tree. I'll give us a more formal definition later on, but right now just know trees contain no cycles. I also want to talk about function composition. We worked on this a little bit in college algebra, and I want to go over it again. So, friendly reminder that if I have 2 functions, f of x and g of x, then the composition of f and g of x is if I substitute in g of x into f. So now we're going to focus a little bit more on the domains of composite functions. So the domain of a composite function, f of g of x, is the set of those inputs in x in the domain of g for which g of x is in the domain of f. Okay? So what we're basically saying is that x has to be in the domains of both functions, kind of like the intersection, or it won't be included. So let's take a look at these 2 examples. So f of x is x squared plus 1. This is a quadratic equation, right? Its graph is a parabola. Its domain is from negative infinity to positive infinity, right? That's an interval. We aren't going to be working with these in discrete math, but this is a great example. Then for g of x, this is a linear equation, right, with negative slope. It's going to look like it's going downhill. Its domain is also from negative infinity to positive infinity. So because they both have the same domain, the domain of our function is going to be negative infinity to positive infinity, and I will show you why. So let's take f composed with g of x. This is going to be f of g of x. I like rewriting it this way because it helps me remember I'm substituting in g of x for x in f. So this gives me negative 3x plus 2 squared plus 1. I substituted in g of x in for f. Now I have to FOIL this out and add 1. I get a positive 9x squared minus 6x plus 4 plus 1. So I get 9x squared minus 12x plus 5. This is our composition function, and it's a degree 2 function like f, so it's a quadratic equation. So its domain is going to be from negative infinity to positive infinity. Cool. So for example 2 here, I have that f of x equals x squared and g of x equals the square root of x. The domain of x squared, as we've talked about, it's a quadratic. Let me switch colors. Its domain goes from negative infinity to positive infinity. But what about the domain of g of x? G of x is the square root of x. Okay. Well, I know I can only take the square root of positive numbers, otherwise they become imaginary, right? We're working with the real number system here. So its domain goes from 0, because the square root of 0 is 0, all the way to positive infinity. So its domain only includes the positive numbers. So let's see what the domain of our function composition is going to have to be. All right, I have f of x, f of g of x is the square root of x squared. Well, square roots cancel out square roots, so I just get x. This is a linear equation whose domain would typically be from negative infinity to positive infinity, right? But if I was to substitute in a negative value for x in this as we go through, I couldn't do that, right? I couldn't do that because this would give us an imaginary number, and then it doesn't matter if I square it or not. We aren't in the real number system. So the domain of f composed with g in this case is from 0 to infinity, right? It's where these two would overlap if I was to graph both of these on the number line. Also, one thing I wanted to mention is that you can compose a function with itself, okay? So that would look like f composed with f of x, which is f of x, which we can also denote as f squared. So let's go ahead and do that. So I'm going to take f of x. So I'm going to substitute this in for x. So I've got 1/2 times, substituting this in for x, 1/2 x minus 3 minus 3. So that gives me f squared of x equals 1/4 x minus 3/2 minus 3. We can rewrite 3 as 6/2. So f squared of x equals 1/4 x minus 9 over 2 x. Now, why did I show you this? Well, I showed you this because we need to talk about iterative